Okay, so hi, my name is Laura Rosenbauer. I've been working on studying the effect of water on the energy budget of urban pavements. To start off with a little bit of background information, I'm going to talk about the urban heat island effect, which is one of the main reasons the energy budget is of interest. And basically, this is the phenomenon where cities are hotter than their surrounding rural area. And in addition to just being uncomfortable, this also threatens human health and puts a strain on energy resources as far as cooling demand in cities. And this problem will increase in intensity as populations are predicted to migrate towards urban areas. As of now, about 54% of the global population is residing in urban areas, but this is predicted to jump to 68% by the year 2050. So one of the main things that sets urban areas apart from rural ones are the materials used there. So for example, you'll find a lot of natural vegetative surfaces in rural areas, whereas in urban areas, you'll find a lot of engineered surfaces and materials, including asphalt, concrete, brick, and those sorts of impervious surfaces. And while a lot of research has been done prior to this on the urban heat island effect and urban materials related to that, most of it has neglected to take into account how rain impacts those materials. And so when I was choosing my experimental sites, I was keeping in mind that I wanted to test how they would react to rain. So I chose asphalt, grass, and concrete to get a varied group. Unfortunately, with the models we used to do calculations, the grass was too rough of a surface for us to trust the models. So I'm really going to be focusing on asphalt and concrete today. So for those experiments, I thought it was really important to look at rain because preliminary research has suggested that urban areas actually experience 5 to 10% more precipitation than their rural counterparts. And although, as you can see in the map to the right, most of the effects are experienced downwind of cities, as cities get bigger, which they are projected to do, the rain event moves closer towards the city center. So this is a real area of importance that we want to focus on. So my experimental setup for each site looks like this. The picture you see here is taken on the roof of the engineering building at Princeton, which was a concrete surface. The experiments were run over a 48-hour time span, and each experiment had a period of rainfall in the middle. I actually got pretty lucky where the rain happened to occur in each of my experiments, so I didn't have to simulate any rainfall. You can see each component of the experimental setup here with the data logger on the left allowed me to store all of my data in one place and then transfer it to my computer. And then number 2 on the right, the net radiometer measured the solar radiation from the sun. The weather transmitter actually collected several statistics. It told us the rainfall amount, the air pressure, relative humidity, and the air temperature. And then finally, at the bottom, we have some thermocouples, which work by measuring the voltage difference. You can see a close-up picture here. It has 2 different metal wires, and it measures the voltage difference in order to tell you the temperature. So they're very accurate, which is very helpful. And so we had one thermocouple on the surface to measure surface temperature, and then we had 7 wrapped around the device here, which was a 3D printed cylinder with grooves every 1 millimeter that we could wrap the thermocouples around, and that allowed us to measure the temperature difference very close to the surface over the change in height, which was important in our calculations for the energy budget, which is shown here. And basically, this equation tells us that as radiation comes in from the sun and hits the surface, it causes a change in air temperature, which is represented by the sensible heat flux, H, as well as subsurface temperatures. So because the surface is hotter than below the surface, heat moves down. And that's represented by G, molecular ground flux. And finally, LE stands for latent energy flux, and that's responsible for phase change. So in this case, it's liquid water changing to water vapor through evaporation. Now I'm going to take you through the methods I use to calculate each of these components and then graph them over time to see any trends. So net radiation was the easiest one. That was measured directly by the radiometer I showed you earlier. And looking at the graphs, so they're going to be similar for each of the components. You can see the dotted line in the middle there represents the period of wetness, so it includes both the rainfall period and the time that it took for the surface to dry. And what I did was, in looking at each graph, because it was over a 2-day period, I could look at the time on the day it rained and then compare that to the same time on the next day, which theoretically should look similar to each other. In this case, looking at the asphalt graph, you can see that it's actually, the radiation measured was much lower than the radiation measured on the dry day at the same time. This could be a result of several factors, including cloud cover or a change in temperature, as well as the fact that the sensors, when they're wet, have not as good, the accuracy is far decreased when the sensor is wet. So it's hard to trust the exact values, although you can tell that it's definitely much less than you would expect. And then looking at the concrete graph, this material experienced net radiation differently, as you can see it looks about the same from day to day. I'm looking at sensible heat flux, so this was the change in temperature above the surface. I calculated this from the temperature gradient found from the sensor I showed earlier and multiplying that by the conductivity of air. Looking at the graphs, there's a similar trend in the asphalt of lower readings than on the day of rainfall than the dry day. You can see you would expect it to be somewhere closer to the levels you see on the dry day. In concrete, however, the values when it was wet are higher than the values when it was dry, which is somewhat unexpected. You would think that that's similar to asphalt, the heat flux would be lower. This can be attributed to the inaccuracy of the sensors when wet, or any cloud cover that may have occurred on the second day. Moving on to ground flux, this was the energy transfer between the surface and subsurface. I calculated this using a force restore equation, which was a function of conductivity, heat capacity, specific heat, and density of the ground surface. I have that equation at the end if anyone wants to see it. And then once again, the asphalt continued to show lower values when wet than when dry. And concrete also showed lower values. So this was a case where they both matched up and showing lower values when wet than when dry. Finally, looking at latent energy flux, which is responsible for the phase change of evaporation. This value is negligible on dry surfaces because you need to have liquid water there for evaporation. So I only have graphs showing during the wet period. But this was solved for using the relative humidity, temperature, and the transfer coefficient. And I also have that equation at the end if anyone's interested. So looking at these graphs here, again, they're only over the period of wetness. You can see that obviously the latent heat transfer increased as the more water evaporated. So conclusions that we can take from this data are that my experiments have supported the theory that rain does have a significant effect on urban surfaces and the way energy is distributed in that urban environment. Although I can't say with any certainty if it's consistent across materials, as in some cases it was, but in others it showed difference. So more research would have to be done, and more repeating the experiments would be extremely helpful, as well as using more advanced measurement devices for increased accuracy during those periods of wetness. I've also learned that this is a highly complex area of study. There are a lot of different aspects to it and things that I could not take into account during my short research period, such as the different surface geometry of urban areas. You have skyscrapers, and they can cause shadows, or they can reflect heat between buildings that would otherwise just escape through the atmosphere. So there are a lot of other aspects that should be taken into account. But ultimately, the goal of this research is to find ways to use this to our advantage in building new cities, as there's still a lot to be built as more people are moving towards cities, and we have a great opportunity to make them as sustainable as possible and hopefully mitigate the urban heat island effect as much as possible. So with that, I'd like to thank my mentor at Princeton, Dr. Elie Bouzid, for all of his help, as well as grad student at Princeton, Haben, who helped me set up all of my experiments and get started with MATLAB, which is really helpful, and the UWIN program for their financial support. And if you have any questions, I'd be happy to answer.